my friends, I'm coming at you today. I'm trying to prepare you for exam number 1. This is a practice question for exam number 1 over material properties. What kind of question could you see? Okay. In this particular problem, we're given a graph. When you're given a graph with all the dimension, the scale there and the grid lines on it, that probably means that we're going to have to actually read some values off the graph. Okay, it's not as much calculating it as it is coming up with some values, reading it directly from the graph. Now we're going to take those values and we're going to do some calculations over here. But what they're asking us for is part A, B, C, D, and E about a specimen. Let's just go through it and see how many, could I ask you more than this? Yes, I could ask you many more questions than this. But this is just some of the questions that I could ask you about a typical graph such as this, okay? Now you'll notice in this graph that there's two portions. A straight portion here, and then there's some portion right in here. It's a little bit tricky to determine like where yield stress is, like where exactly does it go from being linear or proportional to nonlinear, okay? And then it looks like it goes kind of linear again. So number 1, find the modulus of elasticity. That one's easy. You can do that anywhere on the initial linear portion of the curve. So from here to, I don't know, anywhere in here, right, is okay to calculate the modulus of elasticity. Now the modulus of elasticity, what is that? That is E is equal to rise over run, right? Rise is stress. Run is strain, okay? And remember, this is unitless down here, so the units on this are going to be in KSIs, okay? So just pick your 2 points, okay? And I would pick a point where, you know, it intersects one of the lines. It was nice if it intersects exactly on one of the corners. This one doesn't do that. So I'm going to pick right here. Now, do I have to pick right there? Could I pick right here? Yes. Any one of these places, right? The rise or the run should be the same proportion. It should give the exact same value, okay? So I'm just going to pick right there, okay? And then where does that guy intersect? Well, on the bottom it intersects at 0.002, so I know that guy. Okay? And on the top, the question is what is that number right there? Now, to me, it looks like it's just slightly less than halfway. So I'm going to call it, if halfway is 12.5 between 10 and 15, I'm going to call that 12. Okay? So 12 KSI. And if you have one of these kinds of problems on the test, there needs to be some kind of plus or minus leniency because you are just reading it off the graph. Is that perfect? Probably not, but it's really close. Okay? All right, so what is that? On 12 divided by 0.002 is equal to, okay, 6,000. Okay, so the modulus of elasticity is 6,000 kips per square inch. Okay, again, that's just read off the graph. Part B, what is the maximum tensile force applied without permanent deformation? Okay, use the 2% offset rule. Okay, so the 2% offset rule. When you take a test with one of these, I highly recommend that you have a straight edge. Let me see if I have a straight edge. I do have a straight edge, okay? And what you want to do, what is the 2% offset rule? Now, it's not the 2%, it's the 0.2% offset rule. Somebody told me in my videos, you're bad about not putting a 0 in front of your decimals. Yes, I am. So you're just gonna have to get over that, okay? What does the 0.2% offset rule say? It says take a point at 0.002, right? 0.2% is 0.002 divided by 100, right? And then draw me a parallel line, okay? So look here. Go over here at one box, go over two boxes, right? So go up to the next one, go over 2 boxes, 1, 2, okay? Go over to the next point, go over 2 boxes. 1, 2. Okay? And you should be able to construct yourself a pretty good line through there. Like that. Okay? Now what does that do for me? That is a way, now remember, these are very exaggerated graphs, but that is a way to estimate what is my new yield stress, because yield stress is the point where it goes from being linear to nonlinear. We talked about this in the video, that some industries, instead of using a 0.2%, will use a 0.1%, really, and tighten that up. But most of us, for these kind of materials, we just use the 0.2%. Now, what do you do for that? You take that and you read that across, okay? So let's read that across. Let's get very straight as we possibly can here, okay? Okay, and that will give us our new yield strength. That's sigma y, sigma yield, okay? So our yield stress for this particular material here is going to be, what would you call that? Again, that's not quite halfway. It's a little less than halfway. So 26, let's call it 26. Okay? If halfway is 27.5, I think it's a little less than that, probably 26. It's pretty good. Okay? So 26 KSI is what I'm going to call my yield stress. Now it says find the maximum tensile force applied without permanent deformation. Okay, what would be permanent deformation? Now remember, what I'm doing is I'm applying this way here, right? I'm applying force, right? And this way here, what I'm getting from that is deformation. Okay? And at this point right here, okay, according to my yield stress, yield means that's the point at which I'm starting to get permanent deformation, okay? So I want to stay below that if I'm not permanently deformed. So how do I know what the force is to get to sigma y? Well, what is sigma y? What is sigma stress? Sigma is force divided by area, okay? Now we have to know something about our specimen here, right? Maximum tensile force applied without permanent deformation. So our specimen is over here. It has a 2-inch diameter, okay? Which means that it has an area of pi times r squared, right? So, oh, this is easy. I can do this one. The area is equal to 3.14159 inches squared, okay? So if we're looking for the force, right? If we know that sigma is 26 kips per inches squared, paying attention to units here, it's got to be equal to force, that's what I'm looking for, divided by the area, 3.14159 inches squared, right? And when I multiply this on the other side, the inches squared are going to cancel out. And so it's going to leave me F in kips, isn't it? It's always important to know what your units are, right? So here we go. Clear. 26 times pi equals 81.68. Okay? So as long as I don't put more than 81.68 kips on that specimen, I'm not going to have permanent deformation. When I take the load off of it, it should go back to where it came from, right? So there's your answer for part B, okay? This was part A up here. Okay. Hey, at least we didn't get a 0 on this test. We got some of it right, yeah? Okay, part C says 15 feet long, a 2.53 diameter rod is subjected to 150 kips. How much will it elongate? Okay, so this we're going to assume that this is the graph for that material, okay? So how much will it elongate? So step one, we got to find out how much stress it's going to have on it, okay? So step one is stress is equal to pi times r squared, which is 2.53, but that says, boy, that's a common mistake. How many times do you put diameter in for radius? About 1 million, okay? Divided by 2 squared. So pi r squared, that's the area, right? And then what is the area? What is that divided into? Subjected to 150 kips. 150. Okay? And that's going to give us kips over inches squared or KSI. So let's do that. Let's go 150 divided by pi divided by 2.53 divided by 2 parentheses squared equals 29.84. Whoop, not inches. KSI. Okay, so what did we just find? Okay, subjected to 150 tensile load, it will elongate how much? Now we assume that's under load, okay? It's under load. Now, 29.84, where was yield? At 26 KSI. We'll do this a couple of different ways, right? We'll do this under load, okay? We'll just call this part C1, and then part C2 is after load is removed, okay? That will be permanent deformation once you take the load off of it, because what? 29, right? 26 was what? 26 was in elastic region, right? Anything below that. So we're in the plastic region. We are going to have permanent deformation, okay? So up here, if we come across here, there's our number, right? This is 29.84, okay? What we want to know is what is this number here, okay? We want to know is what is that number down there. Now this is a point where you want to let the math do this for you and not so much just guessing the numbers off your graph, okay? So one of the things that we can do, because this is kind of a linear portion curve over here, we can do this, right? Let's say it goes through that intersection there and it goes through that intersection there, okay? So I can come up with the slope of that line, can't I? Okay, so rise over run is going to be what? I don't know. The rise over run on that line is going to be, the rise is 5 divided by the run is what? 0.002, right? Right, 001, 002. Okay, so the slope there is going to be 5 divided by 0.002, okay, 2,500. So here's another way to look at that. If the difference between, 30 and 35 is 2, right, which is that, then what's the difference between 29.84 and 30? Because this is on a linear line here, right? So the difference between that, right? So we're going to do this. We're going to do 30 minus 29.84 is to, I don't know, as 5 was to 0.002 or 2,500, okay? And so what is X? And now X, what is that going to do? That's going to give us, X is going to be this little distance right there, okay? So I've got to take, whatever I get for X, I'm going to take 30, no, I'm sorry, that's not right. X is going to be this distance right here, isn't it? It's going to be that. So whatever I need to do, whatever I get for X, this is X, whatever I find for X, I need to subtract that from 0.008 to get the deflection there, don't I? Okay? So let's see what that is. 30 minus 29.84 is equal to 0.16, okay? And then divided by 2,500 equals 0.000064. 1, 2, 3, 4, 6, 4. Okay, so what do? Remember, that's this distance here, so I'm going to take 0.008. So 0.008 and subtract from that 0.000064, which is equal to what? 0.008 minus answer equals 0.007936. And what is that? That's inches per inch, okay? Now there's about 100 ways to do that, right? It's just a linear interpolation there, okay? So that right there, right, is the strain on that piece. Now, I could read that if I'm under load, that's what the strain is. That's in inches per inch, right? So how can I calculate the total strain on that? Well, the thing was how long? It's 15 feet long. That's a long piece, isn't it? 15 feet times 12 inches is 180 inches. So it's 180 inches, and every inch stretches that much. So the total elongation times 0.007936 is equal to 1.2428. So while it's under load, the total deformation would be 1.428 inches, right? So the thing would be 180 plus that long while it's under load, right? Now what happens if I take the load off of it, right? What happens if I take the load off of this guy? What's going to happen? Well, if I take the load off, remember, I'm going to have elastic recovery, okay? So from this point right here, this is where it was stressed to, I'm going to have this here, okay? Okay, so what is this guy right here? This over here, this amount right here, that's called the elastic recovery, okay? And this part over here, where it's permanently deformed, is called the permanent set, okay? So we need to calculate what is that number right there. And again, you don't want to do this by just reading it off the graph. You want to calculate what is that number. Because we know the slope here, right? Then this is a parallel slope. We can calculate from that what that number there would be. Let's see if we can do that. Okay, since these two triangles here are similar, I think we can use that to our advantage here, right? So sigma y was 26 KSI. Okay, so 26 is to what is, let's see, yeah, 26 is this number here, right? Is to this number here. What is this guy right there? What do you think? This is this right here is 0.007. So there's 6.5, and it's probably halfway again between that. So 00625, let's call it 0063. So is to, what does that make this whole bottom down here? If this number here, right, if that number right there is 0.0063, then what is the total length on the bottom of this triangle here? Whoops, this triangle here, sorry. What's that length right there? Well, it goes from 0.002, so that would be 0.0043, okay? So 26, which is this side, okay, is to 0.0043 as, what's this guy? What's this guy? 29.84. 29.84 is to, what's this value here? I don't know. Now when I get this, it's not going to be that value, right? It's going, because I do know what that value is. We just calculated it. That value is 0.007936, right? 0.007936. But what we're going to find is, we're going to find this, the length of that side of the triangle, okay? So let's see, and those, we'll just call that x. So whatever we find for x, we need to subtract that off of this number, and that will give us our permanent set number, okay? So let's see what we get from that. We get 29.84 times 0.0043 equals, divided by 26 equals. So x is equal to 0.004935, okay? And again, that's the length of that side. We're going to subtract that off of this guy, and that's going to give us that permanent set number right there, okay? So 0.007936 minus, answer, equals 0.003, okay? So this right here is at 0.003, okay? So that's once I take the load off of it, it's going to permanently recover to that number right there, okay? But again, that's in inches per inch. So after the load is removed, how much is the permanent deformation going to be? Well, again, it was 15 inches times 15 feet rather times 12 inches, right? It's 180 inches, and then every inch of that is expanded permanently times 0.003. So I get 0.54 inches. So once I take the load off of it, I have a 0.54 inch elongation. Okay? Forever and ever. Okay. Wow. This is a lot of stuff, isn't it? Okay, this is just similar triangles in geometry though over here, okay? So don't let that scare you. This is just linear interpolation. We know how to do that, don't we? Okay? Well, maybe. Okay, number D. Number D. If it is to absorb 550 inch-pounds of energy, okay, without permanent deformation. Okay, now let's see, what does without permanent deformation mean? That means that we need to use what? To calculate this, right, what is the volume, the required volume, okay? So the equation for that is energy is equal to, okay, the modulus of resilience. Remember, there's two moduli. Moduluses, moduli. The modulus of resilience, which is the area under the triangle part of the curve, and then there's the area of toughness all the way out to fracture. Now we don't want fracture here, because if we have fracture, then we're going to have to use toughness. But it said no deformation, so we want to stay in the resilient zone there. Okay, times the volume of the material. So E, it's given, isn't it? So V, right? V has to be equal to E divided by the modulus of resilience, right? And that's going to be this, okay? The volume is going to be 555 inch-pounds. Don't screw up your units here, okay? Divided by, what is the modulus of resilience, okay? The modulus of resilience is take the yield stress, right? Drop you a line straight down. And the modulus of resilience is this whole area underneath the curve, okay? This area here, okay? And what do? We're just going to consider that to be a triangle. So the resilience, the modulus of resilience is 1/2 the base, right? What do we say the base was? 0.0063. No. The whole base is 0 out to 0.0063. Yeah, that's right. So the base is 0.0063 times the height, and the height, is 26, but that's kips per square inch. Look what's on the top up there, inch-pounds. So 26 kips per inch squared, but we want to get rid of kips, so in a kip is 1,000 pounds, okay? So let's do that little calculation there, okay? So let's see. 555 times 2, right, equals, divided by 0.0063 equals, divided by 26 equals, divided by 1,000 equals 6.77 equals 6.77 what? Inches cubed. Okay? So you need 6.77 cubic inches of material to absorb 555 inch-pounds of energy. Okay? And then the last one says, what's the volume before fracture? Okay? The volume before fracture. Same thing, same calculation, except this time we've got V is equal to, this time it's going to be E, energy, divided by modulus of toughness. Okay? So energy, okay, 555 foot-pounds divided by, what is the modulus of toughness? Now the modulus of toughness is the whole entire curve. So it's this part of the curve here, which is the modulus of resilience, which we already have right there, right? So the modulus of resilience is 1/2 the base, 0.0063 times the height. Can we just call it 26,000? 1, 2, 3, okay? Plus what? Plus this over here, okay? So what do we have? Here's this right here is fracture, okay? So now we're talking about the rest of this. Now, to me, what I'm going to do is this, okay? I'm going to make a triangle, and then I'm going to have a rectangle on top of that, okay? Do I know what that is? Yes. This rectangle is from 0063 to 0.010, okay? So how much is that? 0.010 minus 0.0063, right? That'll give me the base, right? So let's see. 0.010 minus 0.0063 equals 0037. 0037, that's the base, times the height, which is to here, which is 26, okay? Times 26. And I'm going to put it into thousands, okay, because that's kips, but I'm going to make it PSI. 96.2, okay? So the rectangle is 96.2 pounds per inch squared, okay? So I got to have that over here, 96.2, okay? And then what's the last thing I need? I need this little triangle right here, okay? How much is that triangle? Well, this is 26, and so this is what? 35, so that distance is what? 9. So 1/2 9, and I'm going to call it 9,000 because I'm going to put it from kips to pounds, okay? So this is the triangle, okay? Times the base of the triangle. That's the same base as it was there, isn't it? 0.0037. Okay? Oh, we got it, don't we, y'all? 9,000 times 0.0037 equals, divided by 2 equals 16.65. Okay? That's the triangle portion. So plus 16.65. Oh, I'm running out of room. So the volume before fracture is going to be what? 555 times 2 equals, divided by 0.0063. Oh, let's don't do that. Let's find that whole bottom part first. So 0.5 times 0.0063 times 26,000 equals plus 96.2 plus 16.65 equals 194.75. And so 555 divided by answer 2.85. 2.85 inches cubed. That's the volume of material I need to keep from fracturing to absorb that much energy, okay? Woo! What do you think? I could have asked you questions about Poisson's ratio, about if it's stretched, what's the new diameter. I could ask you all kinds of questions about this, right? So study up all those potential questions. This is just a little sample. All right, I hope this helps. Hope it's not too confusing. I hope y'all do great on your test. Let's go, team.